Okay, so half-life. Every time, I'm telling you, lots of times when people talk about radiation, they mention something's half-life, which means we should probably talk about what a half-life is. Oh, I need my periodic tables back too if you pass those up. So, thank you. Thank you. Okay, so half-life. Half-life is called half-life because it's a time. So what will be half of its lifetime? It was the idea. But it's a time for half of the atoms to decay. So half the atoms of that radioactive particle decay, that's the half-life. Okay. Now, whether an individual atom decays or not is completely random. Every atom has a chance, a tiny chance every second of falling apart. Okay? And it's completely random about whether it does or not. You can't predict what an individual atom is going to do. But because you have lots of atoms, a pattern actually emerges. Okay? So I'll give you an example that makes the point. Okay, if I had 100 people flipping coins, and they flipped the coin at one flip a minute, and if you got heads, you stayed. If you got tails, you decayed and went away. Okay? After the first minute, how many people would leave? 50, right? On average. Now, you can only trust it when the numbers get really big, like they are for atoms. Okay? But 50 are going to be able to leave. Okay? The next minute, how many are going to be able to leave? I got 50 to stay. I got 50, so I'm going to flip again. Now I'm going to get to 25. Okay? So the amount of people went down. But it was still half the people. If I had started with 50 people, how many people would have been left after a minute? 25. So the half-life, if I'd started with 1,000 people, how many would I have left? 500. Doesn't matter how much I start with, after one half-life, I'm going to have half as much. So what half-life measures, well, let's think about it. If it's got a long half-life, that means it fell apart really, really slowly. If it had a short half-life, it fell apart really easily. You okay with that? So what it's measuring is how stable that nucleus is. It's measuring stability. Because some atoms are stable and some are unstable. So half-lives vary widely. Okay. I've got some. This has got some radioactive isotopes up here, and it tells me things like uranium. Uranium-238 has a half-life of 4.5 billion years. Some half-lives are really long. Uranium's 4.5 billion years. Since the Earth is about 4.5 billion years old, we have about half the amount of the original uranium-238 the Earth started with. About half of it's still left. It's just coincidence, by the way. I picked one that matched the age of the Earth. Okay. But on here, they give the one for element 106. Its half-life is 0.9 seconds. Okay, some of them actually have half-lives that are microseconds. Its half-life is a microsecond. That as soon as you make it, it falls apart. It's not very stable. And that would be these things down here that are all artificial. Because no matter if the universe started with them, they wouldn't be here if half of it disappeared every millisecond. Right? Because there's been a lot of milliseconds since the beginning of the universe. So that's why everything above 92 doesn't occur in nature. They're all too radioactive. Their half-lives are too short. So even if you made them, they wouldn't be here anymore. They'd fall apart. And what they use this for is carbon dating. Okay? Carbon dating. So when you study history, they tell you how long ago that was, when these people died, when they lived. Before there was written work, before there was a written word, they can tell you how long ago something lived. Okay, and they use carbon. Okay? And how do they use carbon? Okay. Well, how do you figure out how old something is? Well, first apart, they don't use just any carbon, they use carbon-14. And here's how carbon-14 gets made. Got lots of nitrogen in the atmosphere. The sun is sending out billions and billions of particles at us all the time. And I said that the magnetic field trapped the positive, the rays that got to us, but neutrons are neutral. So they're not going to be affected by a magnetic field. So they're going to fly through the Earth continuously. And if they hit a carbon atom, there's a chance, or hit a nitrogen atom, there's a chance they can turn that nitrogen into nitrogen 14. They're going to turn it into carbon-14. The neutron hits it, it'll turn into carbon-14. Okay? So the Earth is constantly being bombarded, so carbon-14 is constantly being made in our atmosphere. But it's constantly falling apart too. So we've reached a point where the amount of carbon-14 in the atmosphere is constant. Because just as fast as the sun makes it, it falls apart. Does that make sense? So we've got a constant amount in the atmosphere, so that means living things end up with that constant amount of carbon-14 in their body. Because we eat food, the plants got their energy from the sun, and they got their carbon from the carbon dioxide in the atmosphere. So they're taking the carbon dioxide out of the atmosphere and making it into plant. We eat plant and make it into us. But the carbon-14 should stay the same the whole way through. So our carbon-14 matches the air's carbon-14 because we're living. So if you measure the carbon-14% in our body and the carbon-14% in the atmosphere, it would be the same. But when things die, you stop taking in carbon-14. So when you die, the carbon-14 you have in your body is all the carbon-14 you'll ever have. And over time, it's going to go down. So in order to look for time, they need to see how much that carbon-14 disappeared. The half-life is 5,700 years. So in 5,700 years, half the carbon-14 would be gone. In 10,000 or 11,400 years, 3/4 would be gone, only 1/4 would be left. Right? So what you can do is you can graph the data. This is a graph of the percent of carbon-14 left after how much time. So that you can see that at 50%, it's right at about 5,700. Make sense? And at 25%, it's right about 11,400. Make sense? So all they did was connect all the dots. Okay? So by measuring the amount remaining, they can determine how many half-lives ago it died. Because I can't tell how old it is, they can just tell you when it died. I mean, if somebody said it's got 75% remaining, why, that looks like 2,000 years. Does that make sense? So since we know how fast carbon-14 decays, we can use that to figure out how much we have left, what percent we have left. Now, it won't work forever. What if you had like 2%? Is this graph going to be really good at looking at 2%? Now, because that line flattens out, doesn't it? So if any little error in your 2% is going to make a huge difference in your time. So you can't use it forever. That you can only carbon date to about 50,000 years. That's as far back as it goes. You can only trust it. And actually at 50,000 years, they're going to say 50,000 plus or minus 5,000. Someplace between 45 and 60. 45 and 55. That's the best they're going to be able to do because that flat line. Okay? So how do we know? I keep saying the Earth is 4.5 billion years old. How do I know? Well, uranium has a half-life of 4.5 billion years. How much of that uranium has decayed? That will tell you how old the Earth is. You just draw the same curve for uranium, except it's going to be stretched out a lot. Okay, so reading guide tonight. Have a pleasant day.